Hello, calculus. This is Mrs. Bricky, and I have tested positive for COVID, so I can't be with you forever for like 9 more days. So I'm making this video for you. And so here are the answers that were not in the back of your book. So if you want to pause and snap a picture so you can compare any issues that you have with any of these problems, maybe like circle them on your assignment or put a giant star with them so that we can talk about them when I'm back. I don't want you to turn in any of your assignments because I'm not going to be there to grade them anyway. So just keep them, whatever assignments I assign you, work on them. If you have problems with certain numbers in class, you can maybe talk about them with other students, but I will set aside some time when I am back so that we can go over all the ones you're having problems with. So take a picture of this if you want, and I'm going to go to the next slide. Okay, so this is lesson 1.2, so a little bit more on limits and talking about some continuity a little bit more and talking about a theorem called the intermediate value theorem today. So what we learned about limits last time was how to read them from a graph, and that if we have the equation for the limit that we want to find, that we could use direct substitution. So today we're going to work on a technique for when direct substitution doesn't work. So here are 3 examples to start with. So the limit as x approaches 0 of x over x times x plus 1. So if you tried direct substitution, you would end up with a 0 over a 0 times a 0 plus 1. And so we call that a 0 over 0 form. And it's undefined because you can't divide by 0. So if we try direct substitution on this limit, we end up with this undefined indeterminate amount. So what you might have noticed, whoops, sorry, I don't want my calculator yet. What you might have noticed is that you could reduce a factor of x right there. And you absolutely can do it. And that means that this is equivalent to 1 over x plus 1 with that x value canceled out up there. Those two limits are equivalent. And so now that we've reduced it, we can use direct substitution, because with direct substitution now, if we sub in a 0 here, we end up with 1 over 1, which is just 1. And again, I'm just using direct substitution on the reduced form. So we're going to use that same strategy on the second one. It's a little less obvious because, at first on this one, you may have even noticed that you can reduce an x. We can factor the denominator here. So the limit as x approaches 2 of x minus 2 over x plus 2 times x minus 2. And again, we can reduce that fraction. So this is the same as the limit of 1 over x plus 2. Now, if we had tried substitution to start with, we end up with that 0 over 0 form. So reducing it allows us now to use direct substitution. 1 over 2 plus 2 is the same as 1/4. Okay, on the last one, you might be looking at that numerator and thinking to yourself, oi, can we factor that? For starters, if we do sub in a 1 here, we do get that 0 over 0 form. So we do want to try to factor it. You might remember, and you might not remember, difference of cubes pattern for factoring. It's a minus b, a squared plus ab plus b squared. That's the pattern for factoring a difference of squares. If you don't have that memorized, that's okay. You can either just try factoring it directly by guessing a factor of x minus 1, And if you kind of guess that x minus 1, you could think about what would the leading term have to be. It would have to be x squared. The ending term would have to be a 1. And to get the right cancellation in the middle, we have a negative x squared, so we need a positive x squared. So it's got a plus x in the middle. So you could try to logic your way through the factoring, or the other method you could try if you wanted is long division. And I know long division, is kind of terrible, but on things like this, long division is pretty slick. So we have x to the third, we have no x squared, no x minus 1, and we're trying to divide it by an x minus 1. Think about how many times does x go into x to the third, and we need an x squared. You times by both terms, so that's x to the third minus x squared. When you're doing long division, you subtract. So we get, those two terms cancel. This is a 0x squared plus x squared. I like to go ahead and just bring everything down at that point, and then you just repeat the process. So I have to think about how many times does x go into x squared. So we need an x, and that gives me an x squared minus x. We're doing long division, so we subtract. And that cancels out, and we have an x minus 1, and you can see that the last term would just be 1, and that would subtract to 0, and so we have no remainder. So that's another way you could factor the top of that fraction to get that, to get that x squared plus x plus 1 and the other factor of x minus 1. Okay, well, once we do have that factored, we are taking a limit, and when you're taking a limit, it's okay to go ahead and reduce that factor. So this is the same as the limit as x approaches 1 of x squared plus x plus 1. Usually, if you don't have that fraction bar as a grouping symbol, you usually do want to put your limit, the function you're taking the limit of, in parentheses like that to show that it's the limit of that whole thing. And then we can do direct substitution. 1 squared plus 1 gives us 3. Okay, so we found all of these limits. Last time we looked at graphs a little bit, so I just wanted to talk for a second about what this means. We took the limit as x approaches 0, and we got 1. That means if we looked at a graph of this function, it would have a hole at 0, 1. So the x value we're approaching is 0, and the y value that the limit approaches is 1. And so all of these values that we found are the y locations of the holes. This function would have a hole at 2, 1/4, because we are approaching x value 2 and we got a limit of 1/4. And this one has a hole at 1, 3. So those are all holes on the graphs. Okay, going into a little bit more complicated algebraic limit here. We have the limit as x approaches 1 of root x minus 1 over x minus 1. We are going to use a technique here that is a little bit tricky. It's called rationalizing. In this case, we're going to rationalize the numerator. Rationalize, you've done things like rationalize denominators before. Like if you have 2 over root 2, you times by root 2 to rationalize. We are going to rationalize the top of that fraction. Now, direct substitution, should always be your first try, but if we do direct substitution here, this is a 0 over 0 form. So we have to try another technique. So what we're going to do to rationalize it is we're going to multiply the top and the bottom of this fraction by the conjugate of the top. So the conjugate is the same expression, but with a plus instead of a minus in between. We do conjugates with imaginary numbers sometimes, you might remember, and we sometimes do conjugates with roots like this. Now, it might seem like a weird choice to do that, but we're going to multiply out the top so that you can see why that was helpful. So if we multiply a root x by another root x, that is x. So I'm multiplying together at the top. Root x times 1 is root x. Negative 1 times root x is negative root x, and negative 1 times positive 1 is negative 1. And you can see that the middle root x is canceled out, so our numerator is x minus 1. I'm not going to multiply out the denominator, and the reason I'm not is because since this canceled out in the middle, I'm going to go ahead and erase it so that you can see it better. But since that canceled out in the middle, all I have is an x minus 1. And so we can reduce that fraction and like that, and we have 1 over root x plus 1 left. And so now we can use direct substitution. If we substitute in, we get 1/2. Again, if we graph this function, we would see a hole at 1/1/2. Okay, number 5, the limit as x approaches 2 from the right. So we've got a one-sided limit here of x over x minus 2. Now this one's a little bit different than the other ones we've done. If you do direct substitution here of the 2, you end up with the form 2 over 0. That's still undefined, but it's not the same type of 0 over 0 form that we have had. We can't reduce this. It's a pretty simple little function, and there's not a way. You can't cancel an x out here. That's not okay. You can't cancel something that is having some addition or subtraction in it. You can cancel factors. You can't cancel terms. So this limit is a does not exist limit. If you have a number over 0, it does not exist. However, sometimes multiple choice or for some other reason, sometimes you need to know if the limit is approaching maybe positive infinity or negative infinity. So we're going to talk about how to figure that out. What we want to do in that case is called a sign analysis. So a sign analysis allows us to figure out if this function's limit is approaching positive or negative infinity. So we are finding the limit as x approaches 2 from the positive side. So, on a number line, we're thinking about getting closer and closer to 2, but on this side of 2. So numbers slightly larger than 2. So if you think about that fraction right there, if we sub in a number that's slightly larger than 2, like maybe 2.01, it's always going to be a positive number, right? If we're a little bit to the right of 2 over here, it's going to be a positive number. So that's positive. The new denominator, is going to be, that slightly larger than 2 number, subtract 2. But if we subtract 2 from this number that's to the right of 2, that is also going to be positive. So we kind of just think about whether these numbers are going to end up being positive or negative. In this case, both the numerator and the denominator are positive, so this limit is positive infinity. And again, it does not exist, but it's sometimes good to have more information, like how does it not exist? Well, it doesn't exist because on the right side of 2 we have an asymptote, a vertical asymptote that's approaching positive infinity like that. Okay, going on to example 6. It says discuss the continuity of this piecewise function f of x. Well, we have 2 pieces here, And it looks like the function is defined to be this top piece everywhere except at 3. And at 3, the function takes on the value 5. So I'm going to go ahead and factor that numerator and denominator, or I guess we can't factor the denominator, but I'm going to factor the numerator. That's going to be an x minus 3 and an x plus 1. So, oh, whoops, sorry. I got thinking about that one still. When you factor it, you can see that we can reduce this factor of x minus 3, which just leaves us with an x plus 1. So on this function, as we approach 3 from either side, this function is going to be approaching 3 plus 1, which is 4. So I'm going to write it as a limit. The limit as x approaches 3 is 4. But the graph itself, if x is 3, has a value of 5. So we have this point on the graph at 3, 5, and this limit up here is that we have a hole at 3, 4. So I would say that this function is not continuous at x equals 3. It has a hole and, has that jump, sort of that little jump. So if we thought about what it looked like, it would look like a diagonal line. So essentially it would take on the characteristics of this x plus 1. So it's this line that has a y-intercept of 1 and a slope of 1, 2, 3. And then at 3, it's just got this little hole at a height of 4, and then at a height of 5, it's got this additional point. So our function looks like this. It's not continuous at x equals 3, but it would be continuous everywhere else. All right, number 7 says if g of x is a continuous function, find the value of a. Well, this upper piece is continuous. It's like a parabola of some sort because it's got that x squared term. And this bottom piece is continuous because it is a line. So the only question is this thing connected at x equals 2? So at x equals 2, those two pieces have to connect in order for this function to be continuous. And it's at x equals 2 that they're equal to each other. It's not for all x values. It's for this boundary. At the boundary is what we care about. So we are really hyper focused on the fact that x is equal to 2 for what we need to check. So we're going to sub in 2 for x. 3 times 2 squared plus a. So that's one piece, the piece that is to the right of 2. And to the left of 2, it's x minus 3. So we are focusing on where x is equal to 2. So that would be 2 minus 3. So we sub in our x value. And now we need to just solve for a. Well, 3 times 2 squared is 12. 2 minus 3 is negative 1, and we can subtract 12 to get a is equal to negative 13. So in order for this function g of x up at the top to be continuous, it has to have negative 13 right there. Any other number, we would see a jump. We would see some kind of gap between this parabola and this line. So for a equals 13, those are going to coincide and connect. For any other a value, they will not. Okay. Our next example uses a calculator. So I'm going to pull up my calculator. It says use a calculator to fill in the tables to help find these limits if the function is this function. So first of all, if you do not have a graphing calculator yet, don't panic. you can do this in the Little Scientific one. It's a little bit different keystrokes, but you could. But if you don't have a calculator yet, we'll get you caught up on this one particular skill later, and it's not a big deal. I do have, and hopefully they found it on my desk somewhere, I do have a printout that has the numeric limit approximation sort of steps right there, but we'll walk through them on the screen right now. So the first thing you want to do is input your function. We absolutely could plug and chug this whole thing over and over again, but if we use the table function of the calculator, then we won't have to do as much. So when we put this function into our calculator, there is a fraction bar if we want it. So you use alpha y equals to get that fraction bar. That's just the fraction menu. But if we use that fraction bar, it's going to give us our outputs, our f of x values here in fraction form, and that's going to make it harder for us to get the limits because it's hard, every fraction is going to have a different denominator, and it's going to be a lot easier if we can compare decimal values. So I'm going to type this in with just some groupings. I'm going to do this top group, and then I'm going to use the division symbol, which will look like that, and then I'm going to type in the bottom. Okay, so we have x to the third, go out of your power, minus 3x squared plus x plus 2. So I'm going to end that group. I'm going to hit my division button to get... so now I can tell it the denominator. I'm going to use a grouping symbol around my denominator. X to the third, go out of the power, minus 2x squared, minus x, and then plus 2. So now that I have that input, we're going to go to the table settings. So we're focused on tables here. So the two buttons we're going to use are this window button for that table setting and this button over here on the end to pull up the table. So we first want to adjust the table settings. When you come into this window, it's usually like this, both of them on auto. We want to change that independent variable to ask. So in this way, it'll ask us what x values we want instead of just automatically doing the integers. So once you change independent to ask, you can go to the table itself, and it should be blank because we told the calculator we would like you to ask us the x values. So now I can type in the x values from my table, and the calculator will do a calculation. So that first value in my table, that first y value, is 5.737. And then I can put in the next one, 50.749. And then I can put in the next one, 0.999. So we're kind of seeing what's happening as we get closer and closer to the value 1. Now, if I put 1 into my calculator, I get an error. So that's why we're trying to just get closer, because at 1, it's undefined, so we can't just sub in 1. So let's put those other values in. 1.001 gives me a negative 499.2. 1.01, so we're going farther away from 1 now, negative 49.25, and 1.1, negative 4.238. So this limit, if we look at the table to help us decide what the limit is, we would say that it does not exist because the right limit looks like it's approaching negative numbers, bigger and bigger and bigger, like an asymptote that's going down. And on the other side, on the left, it's getting larger and larger. So we have a situation where we can't say even one of the infinities because the two sides don't agree. So we just have to say that the limit does not exist. Okay, same function, thankfully, so we don't have to retype it in. I can just keep going down my list. Now we want to look at the limit as x approaches 2. So I'm going to put in 1.9. That gives me 0.272. Now 1.99, so getting closer to 2, 0.328, and 1.999. 0.333. And then on the other side of 2, 2.001. That arrow is bugging me, like it looks like it's pointing there for a reason. So 0.334, 2.01. Oh, maybe it's going to make me, maybe it will only let me type in. I'll go back up to the top. 2.01, 0.339, and 2.1, 0.384. So in this case, you can see that if you're looking at the left side and the right side, it does look like they're converging to 0.333, or maybe even you're like, that sounds like 1/3 to me. Why do we check values getting closer instead of just one value? If you were thinking that to yourself, it's because we need to, for a limit, we really need to see a trend to be able to make an educated guess. But part C question says, can a table like this be used to find limits with absolute certainty? That would be a no. Because we're only checking certain values, there could be hidden behaviors that we can't see. So it's not for certain, but using some numbers that are getting closer and closer to the value does help us figure out, or at least a way of giving us a way to make an educated guess about it. Okay, last little bit is to talk about the intermediate value theorem. So the intermediate value theorem in calculus says that if f is a continuous function on the closed interval from a to b, and if k is a value that is between f of a and f of b, then there has to be a value c between a and b such that the function goes through the point ck. So sometimes this theorem feels hard because it's one of those things that's like, I don't know, it's almost like obvious. If I know this is connected, then yeah, I know at some point the function is going to have to pass through that point. We don't know where C is. C might be over here. In my picture, it's right here, but it could be somewhere else. It might go up fast and then down. But there has to be some number in here where it does hit that height of K. It's connected. It's continuous. There's no way. If it's not continuous, then it might have a jump and never hit that value. But if it's a connected, continuous graph, then we have to be able to find that C value. It has to exist. Okay, so when we use this theorem, it kind of has three parts to it. The first thing is that in order to apply this theorem, we have to state that the function is continuous. Once we state that, we have to show that k is within range. It has to be between f of a and f of b. If we're looking for a k value like 13 that's way above, there's no guarantee that the function ever takes that value. So we do have to verify that k is between a and b. And then once we verify those two conditions, then we can say that yes, there exists some c value. So that's our conclusion part. So we have to show number 1 and number 2, and then we can state the conclusion. So let me show you how that works. Question 9 says, does the intermediate value theorem guarantee a C value on the given interval? So for part A, we have function f of x equals x squared minus x. F of c is 12, and our interval in question is from 0 to 5. Well, first of all, function f is a parabola, and a parabola is continuous everywhere. It's a U-shape. It's continuous. You don't have to do any fancy pants explaining of that. You can just say f of x is continuous on 0, 5. Because it's true, and it's a parabola, and you know it's a parabola, and we know parabolas are continuous. So we've stated condition 1, that our function is continuous. So for part 2, we have to show that 12 is between f of 0 and f of 5. Well, for this function, f of 0 is 0 squared minus 0, so that's 0. And f of 5 is 5 squared, which is 25, subtract 5, which is 20. So our C value 12 is definitely between those two numbers. 12 is definitely between 0 and 20. So that means we can state the conclusion. So we stated that f is continuous. We showed that we showed that 12, the k value, is between our two function values. For the conclusion, we would just say something like, the intermediate value theorem guarantees a C value on 0, 5 such that f of c is equal to 12. And it probably will feel really weird the first few times you do these, but then you get used to how you have to word it and stuff, so it'll be fine. And we'll have tons of practice of this. All right, so those are the 3 parts you have to go through sort of to show that you have a C value. It's actually easier, it turns out, if there isn't one. So we've got function g, x squared minus 4 over x minus 2. G of c is 4, and we are on the interval from 0 to 3. And if you look at this function right here, you might notice that there is a vertical asymptote or some behavior at 2 that makes this function not continuous. And that's what we would just say. We would say g of x is not continuous on 0, 3. The intermediate value theorem does not apply. And you could say there's a vertical asymptote at 2 if you wanted, or you can just say, hey, this thing's not continuous. Okay, so this is one example of when the intermediate value theorem does apply, and one example of when it does not apply. Sometimes there'll be a follow-up question like, if the intermediate value theorem applies, can you find the actual C value? So we're going to use this example 9a to find the C value. Well, when we're using the intermediate value theorem, we're saying that f of c has to take on the value 12. Well, f of c, that means plug c into the function f. Well, that would be c squared minus c is equal to 12. And we're going to factor this. So subtract the 12 to get it equal to 0. If we factor it, we get c minus 4 and c plus 3, which gives us 2 potential answers. However, negative 3 is not in the interval that we are focused on. We are focused on the interval from 0 to 5. So c is equal to 4, and f of 4 is equal to 12. So we found our C value. Okay, here is the lovely assignment. It starts on page 39, 1.2, 1 through 12, 21 through 32, 33 through 45, only the odds, but also skip 41, and then 46 through 51 all.